Hello everyone. Today we are here for discussing an essential tool in understanding complex scientific and engineering concept, that is analogies. Analogies help us relate unfamiliar ideas to familiar ones, making learning easier and more intuitive. In chemical engineering, analogies play a crucial role, especially in transport phenomena, where we deal with momentum, heat, and mass transfer. One of the most famous analogies is the Reynolds analogy, which draws a parallel between momentum and heat transfer in turbulent flow. Similarly, the Chilton-Colburn analogy extends this concept to include mass transfer, highlighting the deep interconnection between these three transport processes. By using these analogies, engineers can simplify complex mathematical models, make reliable predictions, and optimize industrial processes. Throughout this presentation, I'll explore these and other analogies, showing how they help us bridge gaps in understanding and apply theoretical knowledge to real world applications. So let's dive into this fascinating world of analogies in chemical engineering. As stated here, there are four questions which we typically need to answer before we start studying analogies and their equations, which are: what are analogies? What is the physical significance? What are the applications? And why do we have to study them as chemical engineers? So, let's try to understand each of these questions. Analogies like the Reynolds analogy and Chilton-Colburn analogy provide a way to understand and correlate different transport processes, which are momentum, heat, and mass transfer, which often behave in similar ways under turbulent conditions. The Reynolds analogy suggests that the mechanism governing momentum and heat transfer are similar in turbulent flow, whereas the Chilton-Colburn analogy extends the Reynolds idea to include mass transfer, showing that all three transport phenomena can be related using dimensionless groups. Now, what do these analogies do? They simplify complex mathematical models and provide a unified approach to solving problems in fluid flow, heat exchange, and mass transfer. Instead of solving separate equations for these three, engineers can use these analogies to estimate unknown parameters using the known ones. Example: if heat transfer data is available, the mass transfer coefficients can be estimated using the Chilton-Colburn analogy. Now, what are the application of these? Very first, as we just had a look into it, which is simplifies design equations. Second one is optimizes industrial processes. Used in the design of heat exchangers, cooling towers, distillation columns, and chemical reactors. It helps in predicting heat loss, fluid behavior, and material diffusion rates efficiently. Third one, it reduces experimental effort. Conducting separate experiments for heat and mass transfer can be exhaustive as well as expensive. Hence, these analogies allow engineers to use existing experimental data to predict behavior in different scenarios. Fourth, it enhances process control and efficiency. Understanding these analogies helps improve energy efficiency in thermal systems. Example, in combustion systems, knowledge of heat transfer analogies helps in controlling temperature distribution for fuel efficiency. Now, answering the most important questions. Why do we have to study them as a chemical engineer? Hence, by using Reynolds and Chilton-Colburn analogies, engineers can develop simpler, cost-effective, and efficient solutions for problems involving momentum, heat, and mass transfer, making them indispensable tools in chemical and process industries. Now, before understanding what these analogies are in terms of their equations, we need to understand the individual meaning of each term which is involved in these. So now let us have a look at the dimensionless groups and let us try to understand them. Now let us have a look at the dimensionless groups which are needed for us. Very first is Reynolds number. The Reynolds number is a dimensionless quantity used in fluid mechanics to predict the flow regime of a fluid, whether it is laminar or turbulent. It is defined as the ratio of inertial forces to viscous forces in a fluid flow. The formula, as stated, is rho v L by mu, where v is the velocity, L is the characteristic length, rho is the fluid density, and mu is the dynamic viscosity of the fluid. The interpretation can be taken as low Reynolds number is generally for flow when it is laminar, meaning it is smooth and orderly. A high Reynolds numbers typically indicates the flow is turbulent, meaning it is chaotic and irregular. And there's the third one, which is the transitional state. Reynolds number is essential for determining whether fluid flow will exhibit characteristics like turbulence, which affects various engineering applications such as pipe design, aerodynamics, and heat transfer. Now, the second dimensionless group or number which we are going to study is Prandtl number. The Prandtl number is a dimensionless quantity in fluid mechanics that relates momentum diffusivity to the thermal diffusivity of a fluid. It is used to characterize the relative thickness of velocity boundary layer to thermal boundary layer in fluid flow. The formula for Prandtl number, as stated, is Cp mu by K, where Cp is the specific heat, mu is the viscosity, and K is the thermal conductivity. Alternatively, the low Prandtl number suggests that thermal diffusion is more dominant than momentum diffusion, which is typically found in gases like helium or air at high temperatures. The case where Prandtl number is greater than 1, this indicates that momentum diffusion is more significant than thermal diffusion, which is commonly in cases of liquids. Whereas when Prandtl number is around 1, this is a typical for fluids like air at room temperature, where the rates of momentum and thermal diffusion are comparable. The Prandtl number helps us to determine the behavior of heat transfer in boundary layers and the rate of convective heat transfer. Now let us move to the another dimensionless group or number, which is Schmidt number. The Schmidt number is a dimensionless number used in fluid mechanics and mass transfer to describe the relative rates of momentum diffusion and mass diffusion in a fluid. It is particularly useful for analyzing the transport of species in a fluid. The Schmidt number is defined as ratio of momentum diffusivity to mass diffusivity, which is equals to mu by rho d, where mu is the viscosity, rho is the density, and d is the mass diffusivity. In cases where Schmidt number is less than 1, indicates that mass diffusion dominates over momentum diffusion, which is typically seen in gases. The cases where Schmidt number is greater than 1 indicate momentum diffusion dominates over mass diffusion, which is common in cases of liquids, especially those with higher viscosities and lower diffusivities. The cases where Schmidt number is approximately equals to 1, the rate of momentum and mass transfer diffusion are similar, which is often the case for fluids like air under normal conditions. The Schmidt number is used in the study of convective mass transfer, such as in a process involving the movement of gases or solutes through a medium. It helps engineers and scientists predict how well a substance will diffuse in fluid relative to how easily momentum is transferred through the same fluid. Now let us start understanding about Stanton number. As you can see here, we have written it is for two cases. One is for heat transfer and the other one is for mass transfer. So let us start with the first one of heat transfer. Stanton number is a dimensionless quantity used in heat transfer to describe the ratio of heat transferred to the fluid to the thermal capacity of the fluid relative to fluid's flow velocity. It is an important parameter in the study of convective heat transfer, particularly in boundary layers where heat is transferred between a surface and a fluid. The formula as given is H by rho CpV, where H is the convective heat transfer coefficient, rho is the density of the fluid, Cp is the specific heat capacity at constant pressure, and V is the velocity of the fluid. Alternatively, it can also be written in terms of Nusselt number, which can be given as Stanton number equals to Nusselt number by Reynolds number into Prandtl number. Now, the Stanton number provides insights into the efficiency of heat transfer in fluid flow. A higher Stanton number indicates more efficient heat transfer, meaning that more heat is transferred per unit of fluid flowing past a surface. It is particularly useful in characterizing convective heat transfer in processes like cooling of electronics, heat exchangers, and even atmospheric heat transfer in meteorology. In general, the Stanton number is a key parameter in understanding and optimizing heat transfer in practical engineering systems and involving fluids. Now, let us look through the mass transfer perspective. In mass transfer, the Stanton number is used to describe the rate of mass transfer in a fluid flow, analogous to its use in heat transfer. It relates the rate of mass transfer from a surface to the fluid's flow velocity and its mass diffusivity. As the formula is given as K by V, where K is the mass transfer coefficient and V is the velocity of the fluid. Alternatively, Stanton number here can be explained in terms of Sherwood number, Reynolds number, and Prandtl number. The Stanton number in mass transfer represents the ratio of rate of mass transfer to the rate of convective transport of the fluid. A higher Stanton number means more efficient mass transfer, which indicates that more solute or mass is being transferred per unit of fluid moving over the surface. It is especially useful in processes like gas absorption, distillation, filtration, and chemical reactions. In industrial processes, where understanding how quickly a solute diffuses into or out of fluid is crucial. Hence, the Stanton number in mass transfer helps quantify how well mass is being transferred between a fluid and a surface, playing a critical role in the design and analysis of processes involving mass transport. Now, since we have had a look at all the dimensionless groups which we are going to overcome in this chapter, now let us have a look at the equations which we are going to study and which we are going to apply in upcoming numerical problems. Before moving forward, let us have a look at friction factor 2. The friction factor is a dimensionless quantity used in fluid mechanics to quantify the resistance to flow due to the viscosity of the fluid and the roughness of the surface through which the fluid is moving. It plays a significant role in the calculation of pressure drops in pipes, ducts, and other flow systems. The friction factor, often denoted by F, is a critical component of Darcy-Weisbach equation, which is used to calculate head loss due to friction in a pipe, where delta P equals to F into L into rho V square divided by 2D, where delta P is the pressure drop, F is the friction factor, L is the length of pipe, D is the diameter of pipe, rho is the density of fluid, and V is the velocity of the fluid. For laminar regions, the friction factor is directly dependent on Reynolds number, where F equals to 64 by Re. The significance of friction factor is it helps to determine head loss or pressure drop in piping systems, which is critical for designing purposes. The friction factor reflects how easily or difficult the fluid flows through the pipe, and it helps in minimizing the friction factor is important to improve the efficiency of fluid transportation systems. Now, let us have a look at the equations. The generalized form of transport analogy is 1 by 2 F delta equals to Stanton number for heat transfer multiplied by Prandtl number into delta T, which is equals to Stanton number for mass transfer into Schmidt number into delta C. Now looking at the assumptions Reynolds analogy considers, which is delta equals to delta T equals to delta C and Prandtl number equals to Schmidt number, which is equals to 1. Hence, the final equation for Reynolds analogy turns out to be F by 2 equals to Stanton number for heat transfer equals to Stanton number for mass transfer. Now, looking at Chilton-Colburn analogy, where delta by delta T equals to Prandtl number to the power 1 by 3 and delta by delta C equals to Schmidt number to the power 1 by 3. Substituting these in the generalized form of transport analogy equation, we get F by 2 equals to Stanton number for heat transfer multiplied by Prandtl number to the power 2 by 3 equals to JH, which is Colburn factor for heat transfer. In a similar manner, when F by 2 equals to Stanton number for mass transfer multiplied by Schmidt number to the power 2 by 3 is equals to Jm, which is Colburn factor for mass transfer. Since we have had a look at the equation and understood the physical significance and importance of studying analogies, let us try to apply them by solving some theoretical as well as numerical questions. The very first question is a theoretical question, which is distinguish between Reynolds and Chilton-Colburn analogy. Now, here I have created a table which defines the aspect and its comparison for both the analogies. Let us start with definition. Reynolds analogy relates momentum transfer to heat transfer, whereas Chilton-Colburn analogy extends the Reynolds analogy by incorporating mass transfer and modifying the heat transfer correlation. The equations are same as we had a look at them just a minute before. The assumptions goes as follows. Reynolds analogy generally take place at high Reynolds number and assumes that Prandtl number and Schmidt number are equals to 1, which does not consider the pressure gradient effect. Whereas the Chilton-Colburn analogy is a more generalized form and accounts for different PR and SC values. The application of them are: for Reynolds analogy is generally used in basic fluid flow and heat transfer problems, whereas Chilton-Colburn analogy is used in heat and mass transfer problems, particularly in chemical and process industries where Prandtl number and Schmidt number come into picture. Since we have studied everything related to the theoretical aspect of these analogies, it is important to understand what are the limitations for the same. The Reynolds analogy is valid only for gases, and all the properties in both the analogies are estimated at an average temperature. Also, in case of Chilton-Colburn analogy, which incorporates Prandtl number and Schmidt number, there is a certain range defined for both these dimensionless groups. As stated, Prandtl number should be between 0.6 to 60 and Schmidt number should be between 0.6 to 3000 for applying Chilton-Colburn analogy. Also, there are some added geometrical limitations which cannot be stated or defined in this video. Hence, now we have studied all the limitations, all the applications, physical significance of both the analogies and understood how they are important for us to study them as chemical engineers. Now, it is the time to apply them in some of the numerical problems to understand their applications and their uses in a better way. As chemical engineers, studying transport phenomena with the help of analogies not only simplifies our work but also gives us the knowledge of industrial applications and experience of industry which can be done in future when people get into the industry. So, let us now quickly have a look at a few of the numerical problems which we are going to study. We will be analyzing and applying the analogies according to the conditions solving them, and getting to the final answer for the problem asked in the question. Let us move ahead.